Yes, you have to project. You have to go either on a common fine grid. You can go to a fine grid, common fine grid, maybe the finest grid you can get, and that makes the assimilation on this finest grid, and then you have to coarsen all the members.
Do you see an effect of the grid? Do you see a strong effect of the grid in terms of its influence on the country?
No. Yeah, I would say yes, yes and no. Yes and no. It depends, because when we work on that, we introduce some projections on different grid during the assimilation. So we say, okay, I will compute my innovation, make the product with the Kalman gain, and maybe I will project this the Kalman gain times the innovations on a very coarse grid, on a very fine grid, on the grid of each members, and depending on your choice, you will get different results. So
if you have a fixed grid with the nested grid, you would not have to do it.
If you have
Fixed grid.
yes, because
I always find the use of AMR problematic. I'm serious. Because they try it with general circulation dynamics and the turbulent flow. It doesn't make a lot of sense. And the other reason that it would make me nervous here is that wave propagation is very sensitive to bathymetric details. As you coarsen or refine, you're
removing some details.
You're doing the same thing to your bathymetry, and you're losing a lot of the detail. And I really to keep the bathymetry constant, so you start with coarse bathymetry, and as you refine the solution, you keep the bathymetry at the same resolution, or you keep refining the bathymetry. And this is mostly a wave propagation problem, and the wave speed is just given by
the bathymetry. Oh.
Makes it tough. I agree, but I still think like treating bathymetry as, you're not inferring all the bathymetry everywhere. That's not we are always like taking the location. You don't care about that. I just had an issue with the forward model.
I understand. That's right. It creates this jumps on the define. But if you have a solution to that problem, we integrate that into the destination in a way that's easy to activation the forward model. That's the problem.
And maybe it's an issue of practicality that the model is so expensive, and the AMR will make it affordable.
Problem of source identification and prioritization of location in a context geometry
is almost the same problem, I think. Because look, if you take the stream with all the shapes, you change the source, and essentially you're measuring the way the nearest distance to an offset. That is a continuous function, but the predictability is nowhere here.
Yeah.
Just think of the distance between U and V at the midpoint. It's a random thing. And if you know how to smooth that, then you solve it in a different way of physics. But you're varying the source in the presence of complicated offsets. This is really no recipe.
Yeah.
If everything was in 1D domain, I can guarantee you I can make the propagation with the timing as smooth as you want to do. And decrease as fast as but once the geometry is complicated, when you change the source in the reference theater, it's going to be showing up like leading order even if the activity described to. So the problem is really the way the environment complexity is already in the geometry. Even if we are all at the time straight, you're basically measuring the nearest distance to a coast because this is really what we're reflecting. That function is a continuous thing, but the differentiability is something. And this is embedded in the physics. So anytime we're dealing with pure wave phenomena, this is going to be a precedence event, which is really what the physics is. Even if you can
So there is also a question about the accuracy. What is your accuracy you want? Because the data is awful, and you don't need to be super accurate. Yeah.
You have multiple reflections. That function is set, which shows up in, when was the first characteristic arrive, is continuous in the parameters but constant. That's what we have.
Yeah.
So in a sense, you would expect your spectrum to flatten and not to decay more than below order as a brain. Just that. And it's a situation where you start having multiple reflectors that is one of the most areas that which way it bounces first. You have multiple choices.
Yeah. So let's go back to the reduction. So just as a reminder, the last slide of the last equation was the reduction of observation for the posterior distribution. And the question now is, we have the same equation, the exact same equation, and the question now is, can we compute this basis, this matrix V, this very thin matrix V, in an optimal fashion? If we are able to drastically reduce the data, we will compress terabytes, petabytes, or I don't know the size you are using, but we will be able to compress this data a priori while keeping information about the posterior distribution. This is one effect of this kind of technique. The second effect is we will reduce the size of the observation covariance from n by n to r by r. And in the Kalman gain, usually you have to invert the covariance of the noise, and hopefully it will be a small matrix, and you will have to invert a small matrix. And the goal of the second part, in fact, is to define V as the minimum on a manifold. I will discuss what is a manifold of a loss function depending on V, of course, the X or the distribution of X, Y or the distribution of Y, and the data, or maybe not the data. In this context, in fact, I will only work with a linear model, linear Gaussian model, Y equal BX plus E. X and E are Gaussian and independent, and Y, the observation, is also Gaussian. B is a design matrix. It's a fixed matrix. Okay? So we have the observation, that is a fixed matrix time the parameter you want to infer, plus some noise. So this is on one hand. Just for the notation, I will note A of X equal BX. A of X just to be able to extend the approach to nonlinear models. And CRX would be the covariance between the forward model and the input parameter. So we have the full model on one hand, and on the other hand, we have the reduced model, which is W, which is simply equal to VTY or VTBX plus VTE. Everything is Gaussian. Everything is linear. We can compute the posterior distribution analytically. So let's do that. For the full model, we have this. So the posterior distribution is distributed according to Gaussian distribution with mean M star and covariance C star. These are our target. This is our target. This distribution is our target. We want to approximate this distribution by reducing the data. And on the other hand, we have the posterior distribution of the reduced model with a mean that depends on the matrix V, a covariance that depends on the matrix V, that is given by this formula. So this looks very ugly, but I really enjoy this part. I really enjoy it. Why? Because if you are used to linear algebra, you will recognize here some kind of Rayleigh quotient. So when you have a Rayleigh quotient, you will think about maybe we have some invariance property because we have some subspaces, some invariant subspaces of some operators. Maybe we can identify these subspaces. So as a mathematician, when I saw this, I said, oh, maybe there is something here. The first thing we can say is for all invertible matrix M, M of Vm of V capital M is equal to MV, and CVM is equal to CV. So just to go back here to the reduced model, if instead of W I'm considering MW, I will get with M invertible, I will get exactly the same distribution. What does it mean? It means that we can permute the observation, we will get the same distribution. We can rotate the observations, we will get the same distribution. We can rescale the observation, we will get the same distribution. This is somehow reassuring, right? Reassuring. We are happy to have that, because if we permute the observation, we won't. If we have a different distribution, then there would be a problem somewhere. The Newton method. So one issue. So y, let's assume y is large, is in values in Rn, n is huge. We have W, V will be a matrix, a very thin matrix, but very long. So VTY will be very small. So we will go from a huge amount of data to a very small amount of data.
You assume that it exists. You assume that it exists.
Yes. At first we assume that it exists, but then I will introduce, in fact, some loss functions and some particular search space, such that V exists every time. Okay. So, given this invariance property, we cannot use the standard Newton method. Why? Because if we have the optimal solution, then a small perturbation of the optimal solution can still be an optimal solution. That means that the Hessian will be ill-conditioned next to a solution. That also means that we are more interested by range of V than V. Range of V is just a subspace generated by the column of V. So we are more interested in the subspace than in the matrix. And this is a characteristic of Grassmann manifold. So Grassmann manifold is a set of subspaces. So GRN is a set of subspaces of dimension n in a subspace of dimension R in a whoa, it's not clear. Let me read. The set of R dimensional subspace of Rn. Okay. This is very technical. I won't get into the details. Just just remember that our manifold here, or search space here, VM, is a set of subspace and not a set of matrix. And given that this is a manifold, we can use a very smart algorithm on manifold, and this is what we are doing here to compute the optimal solution of the criteria I will introduce in the next section. So, what could be the optimality criteria? And maybe I can ask Youssef. Youssef, what could be the optimality criteria? The Kullback-Leibler divergence between the true posterior distribution and the reduced posterior distribution. So the question you were asking just before. So the Kullback-Leibler, in fact, it quantifies the information lost when the distribution PZ1 is used to approximate the distribution P0. This quantifies the information loss, and it's positive, and the value is always positive, and this quantity is null only if the two distributions are equal. It's an asymmetric quantity, so it's not a distance, but it's pretty close to a distance, and we will use the Kullback-Leibler divergence as a distance in this talk. So we will minimize, in fact, practically the Kullback-Leibler divergence on the Grassmann manifold.